Hello everyone, my name's Chris, aka Suits from Rogue Entity. Today I'm just going to be doing a quick walkthrough of mass so you can get a basic understanding of what mass is, why you might want to use it, why you might not want to use it, and just get our heads around some of the terminology that is used with mass and just entity component systems in general. So what is mass? What is an entity component system? The two terms interchangeable. So mass is Unreal's data-oriented framework, which is commonly referred to as an entity component system. And an entity component system, or ECS, is a software architecture that separates data from behavior. So normally you'll have in a data-oriented setup, which we use normally in Unreal Engine, you'll have your actor, you'll have a base class, you'll have child classes, and that behavior we built in either with components or on the actor itself, and it all lives on each object. So ECS replaces that data structure with separated data to logic. So a data-oriented framework extracts that data from the actor and extracts the logic from the actor and places them in two separate systems. The visualization of the actor is another separate system, and we'll cover that. Data-oriented framework essentially optimizes that data separation and puts it into optimized memory layouts, so it allows it to process the data using all the latest technology and fast access to achieve what is essentially lots of entities. So with the separation of data, your actors then are not, their behavior doesn't come through that inheritance. Your behavior comes through snapping on components, and depending on what configuration of components your entity has is what makes up its class. So why would you want to use mass or any entity component system is you need to optimize your game. You want to have a large number of entities, maybe thousands, and your object-oriented setup isn't just going to cut it. So mass is going to optimize that for you. It's going to put your data into what's called archetypes and chunks, and it's going to allow much faster access to all that data and much faster processing of all that data. And it'll achieve that through the structure of the data, and it'll allow a lot more to be stored in the cache locally, minimize cache waste to almost zero. If you don't know how cache works, I'll cover that in a minute, but essentially that is going to speed up things dramatically for your processing. So the snap-on components sort of thing that I mentioned is what gives the scalability to mass or ECS. I'm talking about generic ECS here, but we're going to go into mass details in a minute. But you don't have that class hierarchy anymore. You can just add a component and you have a new class, and you can do that at runtime. And the structure of that data in the memory is what allows this parallel processing and multiple threads to really work hard on the data more so than they can with object-oriented. So there's a few reasons why you might want to not use mass, and there is some mitigation for these things in mass or ECS, but that separation of the data to the process, which I'm calling their indirect behavior, it can get quite confusing. So the logic of your entities or actors, it's quite separated. So you may have multiple processes that act on one entity or something like that, like not one, but like one similar entity, one type of entity, and it can get quite confusing where the data or the logic's happening for those entities. So I highly recommend starting to use mass. Just document what you're doing. So if you create a processor, put it in a spreadsheet or something and put a description of what that process is doing and maybe what components it's touching. It'll be very helpful later on. This can be avoided quite easily, but if you've got entities that you want to add or remove components all the time, or you need so many different states where you've got to add tags and remove tags all the time, and I'll cover what these components, mass calls components fragments, but I'll get into that next. But if you're adding or removing these data structs all the time, it's going to really affect mass's performance. It does mitigate it through the deferred batching, but it's still quite expensive to constantly change components on a entity. So there's ways around that. Like you don't necessarily need to add and remove components if you're not using them. But just keep that in mind because it's going to come into your assessment of whether to use mass or not. If you don't need a lot of entities or you don't have a lot of simulation that you need to do in the background, like just mass is probably not worth it. Like for starters, if you don't have a lot of entities, like if you've got 30 entities, then the overhead for mass to get set up is probably not even going to give you any performance gain. So just keep that in mind. Sort of similar to what I was talking about before. If you've got too many fragments, this is more like if you've got a whole heap of entities and they've got very different configurations and you've just got heaps of them, it's not going to really be good for mass either, because mass sort of works on putting things into groups of the same thing and processing them super fast that way. If you've got just totally, like say you've got 1,000 entities and they've all got different configurations, it's just going to destroy mass. Like you're just going to have 1,000 chunks essentially, and it's not going to perform that great. Get by that by grouping your components on your entities in a better way. Also, if you're not used to sort of read, write, access, const and all that, it could get quite confusing. When you set up a process, you sort of, every component you say, well, do I want to read this or do I want to write to this? And if you're not used to that, it can get confusing. That's pretty minor, to be honest, but something to be aware of. So let's talk about actual mass terminology now. So just in a normal entity component system, an entity is just an int32. It's just almost commonly an int32. So it's just an ID. It's just a number. It just identifies this entity. So you got entity 0, 1, 2, 3, and 4. You've got 5 entities. For mass, that is a struct. So you'll see it referred to as a mass entity handle. It's just a struct with an int32 in it. So that identifies the entity. And then the components in mass are called fragments, like I mentioned before. But there's also tags, mass tags, and these are just structs as well. So these are your core data structs, and they'll just have, so think of these as like containers for your variables that you'd normally have on an actor. They're now just in a struct, and you can create a fragment for those. So like a transform, for example, on a entity, it might be a fragment, and it'll have, the data inside either a transform or position velocity like I got there. There's also shared fragments. This is more like your read-only data that you might have. It doesn't have to be read-only, but it's like shared data that a whole bunch of entities might have. Like a good one that is built into mass by default is the movement data. So it's like the stopping radius, the radius of the character and all that. It's just generic data that's not going to change, and so it'll be a shared const fragment. And then the mass tags are literally just empty structs, and they're used to filter entities when you want to process them or identify other things. So think of them as almost like a bool or something. Like, does it have this tag? Then I want to do this to it. And that's where the processors come in. So the base class is the mass processor, and you'll create a new processor from that base class, and then you perform any logic that you want to do on those entities in a processor. And you may have multiple processors, and you'll use different phases. So there's different processing phases, which Unreal has, like through its tick as well. But these phases are linked to that tick process in the Unreal Engine, and so you can do a process on one phase and then do a process again for something else on another phase, so you can set data up for other processes. And I'll cover the processes in more detail, but they work by matching entities and filtering the entities through configuration queries. So when you add fragments to an entity, you're essentially creating like what's called an archetype. So an archetype is an entity or groups of entities that all have the same components. So in the example there, we've got entities that have position, velocity, and health, and then we've got some other entities that only have position and velocity, and we've got some other entities that only have position and health. So any of them that are the same get stored in the archetype, and this is just like how it handles optimizing their storage in memory. All those same entities are then divided into chunks, and the chunks allow it to access smaller sets. It's still fixed size, so it knows exactly what it's got, but it just allows it to access smaller chunks. So it can do optimizations such as multi-threading or parallel processing on those chunks. So when a processor gets a chunk, it knows no one else is touching this chunk. This is my chunk. I can write to a value and no one else is writing to that. There's not going to be a confliction in the memory. And the combination of the archetype and chunks allows it, and how it stores that data allows it to access it very fast. So it's all neatly packed in memory, and I'll cover that a bit more in a second. But it can access, because all the data is the same, it can just access it super fast. So this is the processing phase I mentioned. There's several phases there. So if I wanted to set up some data, I don't know, say I wanted to, I don't know, I can't even think of an example. If I wanted to build an array of some sort of data through a processor, I want to do some calculation to it before I then use it in something else, I can do that in the pre-physics. And then in another processor, if I make that the phase for that processor start physics or end physics or something like that, then that data will be done in pre-physics, will be ready for, that other processor in start physics. And that's sort of how you'll need to be aware of the phases. There's no real need to customize these. You can create custom phases. It's all managed by the phase manager, and it's all well done by Unreal, so it's not really, if you need more than 6 phases, you might be doing something wrong, but who knows what people are going to do, so you never know. I think it's just important to be aware of phases, because it's quite common to come up where you need to do one thing before another, and that'll be handy. So the example picture here, I've just slotted in here, is the difference between the object-oriented design and the data-oriented design in memory. If you don't know what cache is like memory that is close to the CPU, so it can just grab it really fast. And just to sort of like an example of how cache works is, like, if you think of level 1 cache, if your hands are the CPU and it's processing stuff, then level 1 cache, it's literally in your hands and you're working on it. Level 2 cache it's on the bench just below you. You can pick it up and it's in your hands now and you can do something with it. Level 3 cache it's on the bench but it's out of reach. It takes a little bit more time to get to it, but it's still super fast. And then, you've got your main memory, which might be like, it's on a shelf, you got to stand up and grab it down, and it's quite, when you're processing stuff super fast, it's quite a bit of extra time to go to main memory. And then I guess the other example of this is your hard drive. It has to go to hard drive to grab something off. It's like it's in the garage or something. You've got to go walk and get it, It's going to take ages. So the way object-oriented design works is it will put an actor in memory when it's going to reference it and whatever's attached to that actor, and that may not be contiguous in memory. So, you're going to have all these things being put into your cache that are different sizes, and they don't fit neatly into, like a cache memory slot. So like that first data might need part of the second, depending on what your cache slots are, like say it's 512 and you got, something that's 720 kilobytes, then it's going to take up over a slot and a half sort of thing. So that next memory slot, anything after that is wasted, and it has to start on the next slot for the next data type, and you end up with all these gaps in your memory. Whereas the data-oriented design is fitting all the same data, one after the other, really tightly packed, and that's how it achieves its fast access and efficient, use of the local cache. It's very overhead view, I know, but it's sort of the main way. And then plus the setup in the software design allows it to, with the batches and archetypes and stuff, allows it to move the data around and keep that tightly packed setup. And if you want to know more, just go out there and search like ECS and how it works. And there's people who explain it way more detail and probably better than me. But yeah, that's an overview of how it all works and how it gets to be so much faster. So the processors, and I'll show you a processor class here. I'm not going to do any coding with this video, but I will in the next one that I do. And we'll do the whole setup, and I actually want to make a project and go through it. So the processors, you just inherit from the mass processor class, and then you override the configure queries and you override the execute. functions and you've got a processor, so you can do whatever logic you need to do. And the configure query, just you declare that's where you do the filtering of what entities you want to process on using the mass entity query, and then that gets pulled in, and you can view that data through something called views, and you can also just access the fragments and process that data. You can have multiple queries per processor, but you sort of got to weigh up whether you have multiple queries or you have multiple processors, and depending on what you're doing. I'll try and get an example of both when I do an example. But that's what a processor looks like. You can see there just overriding the configure queries and adding in a requirement to the mass entity query of what fragment the entity should have. So any entities that have a transform fragment, a move target fragment, a movement parameters fragment, and then also have the tag has destination and also doesn't have the tag stun tag, will then get pulled into this move query, and the logic down below will get processed. So it's just a basic movement one there, but just for an example. But it's pretty basic structure. There's just set ways that you need to access data fragments, and I'm going to go into way more detail later. So this is just for info, quick look at the structure of a process, because I think process part is a bit confusing when you get started. So one thing I will point out is something that's passed into these queries is the entity manager. So the entity manager is what owns all the entities and the archetypes, and also the entity manager will handle all the changes to component fragments and tags that you do, and it does that through a deferred command buffer, which I'll cover a bit more in a sec. If you ever need to access the mass entity manager from somewhere else, like I've had to do it in debug tools that I run, then you can do that through the mass entity subsystem. That's where the entity manager lives. But pretty much if you want to do anything to an entity, it's going to go through, as well as access them, it's through the mass entity manager. All right, so some other terminology that is going to come up is mass traits. So traits, pretty simple. They're just groups of fragments or tags, almost like a blueprint. You know, like if you're going to create a blueprint of a character, you can create like a pre-configuration of fragments and tags to assign to an entity. You can add a trait, and then you can add individual fragments as well. So like it's not fixed or anything like that, but that's just a way of assigning many fragments or tags at the same time. And that's a pre-configuration thing, it's not a runtime thing. Some other terminology you're going to hear is command and signaling with ECS. So the command is what I was talking about before, that mass command buffer. It's used to queue up commands, basically. So when you're processing the way that an ECS system or a data-oriented system processes, you don't want to interfere with what it's doing. It's got the data in a certain point where it's like, I've got access to this data, this is my data, no one's touching it, I've got read, I've got write access, no one else is reading or writing, and it doesn't want to be interfered with. So when you want to do something like change a component, delete or destroy an entity, add a tag, it has to be delayed and it has to be done at the right time in between processing. So that's what the command buffer does. The other one there is the mass spawner subsystem. So that's a subsystem that has all the functionality to spawn and destroy entities. So you'll definitely use that. And then the other terminology that you might hear is signaling, especially if you're not using mass, using something else. You might have to actually configure this. But mass, it seems to be all pre-configured from what I've seen. You may want to do some custom stuff at some point, but it's basically events for all those things that the commands do. So when you add a component, it's going to signal, hey, I've added a component to this entity or these entities. Can you please initialize that? And it sort of is all handled, really. But just be aware that there is that ability to do that, and you may want to tie into that at some point. I haven't had to do that myself yet with mass. And then the third component, or I shouldn't say component, the third area of the entity component system and mass as well, obviously, is representation. So this is what bridges the virtual entity int32 to something that lives in your world. So, you know, like all those fragment data, or, you know, if an entity has a transform, it's what places something in the world at that transforms position that you can visually see. So, it might be an actual actor, instance static meshes, or it can be an Igara visual effect as well. So the other thing that there is representation built into mass, so it's really good too. So it's got all the LOD set up in there. There is some stuff you need to configure for the mass visualization LOD processor in the settings and stuff, but we'll cover that in the next video. But the representation system handles, so distance-based LODs, you can, when you're really close, have an actual actor. When you zoom out, you can have instant static mesh or your VFX, and you can cull that by distance. You can cull that by numbers, so you maybe only want to say, look, I want actors when you're up close, but only a max of 50, and it will keep the others at instant static meshes or whatever else you're using. If there's too many on the screen, it's really can optimize it quite nicely. So that's really all I've got for this quick understanding mass video. I hope this helps you get your head around some of the terminology for mass. In the next video, I'll get into how to set it up, and we'll start on coding a basic project that you can have as an example project to reference to. I want to thank all the Patreons for continued support while I'm off been learning this stuff and doing whatever. Really appreciate this ongoing support, and I will see you all in the next video. Thanks for watching.